Mapping. The transformation of data from main memory to cache memory is referred to as a mapping process. Three types of mapping procedures are: 1. Associative mapping. 2. Direct mapping. 3. Set associative mapping. A specific example of a memory organization as shown in figure is used for discussing three mappings. The main memory can store 32K words of 12 bits each. The cache is capable of storing 512 of these words at any given time. The CPU communicates with both memories. Associative mapping. The fastest and most flexible cache organization uses an associative memory. The associative memory stores both the address and content, data, of the memory word. This permits any location in cache to store any word from main memory. The diagram shows three words presently stored in the cache. The address value of 15 bits is shown as a 5-digit octal number, and its corresponding 12-bit word is shown as a 4-digit octal number. A CPU address of 15 bits is placed in the argument register, and the associative memory is searched for a matching address. If the address is found, the corresponding 12-bit data is read and sent to the CPU. If no match occurs, the main memory is accessed for the word. The address data pair is then transferred to the associative cache memory. If the cache is full, an address data pair must be displaced to make room for a pair that is needed and not presently in the cache. Several replacement policies like first in first out, FIFO, is used for this. Direct mapping. Associative memories are expensive compared to random access memories because of the added logic associated with each cell. It uses a random access memory for the cache. The CPU address of 15 bits is divided into two fields. The 9 least significant bits constitute the index field, and the remaining 6 bits form the tag field. The main memory needs an address that includes both the tag and the index bits. The number of bits in the index field is equal to the number of address bits required to access the cache memory. In the general case, there are 2K words in cache memory and 2N words in main memory. The N-bit memory address is divided into two fields, K bits for the index field and NK bits for the tag field. The direct mapping cache organization uses the N-bit address to access the main memory and the K-bit index to access the cache. Each word in cache consists of the data word and its associated tag. When a new word is first brought into the cache, the tag bits are stored alongside the data bits. When the CPU generates a memory request, the index field is used for the address to access the cache. The tag field of the CPU address is compared with the tag in the word read from the cache. If they match, hit, the desired data word is in cache. If they don't match, miss, required word is read from main memory. It is then stored in the cache together with the new tag, replacing the previous value. Disadvantage: the hit ratio can drop considerably if two or more words whose addresses have the same index but different tags are accessed repeatedly. Set associative mapping. Set associative mapping is an improvement over the direct mapping organization in that each word of cache can store two or more words of memory under the same index address. Each data word is stored together with its tag, and the number of tag data items in one word of cache is said to form a set. An example of a set associative cache organization for a set size of 2 is shown in figure. Each index address refers to two data words and their associated tags. A set associative cache of set size K will accommodate K words of main memory in each word of cache. When the CPU generates a memory request, the index value of the address is used to access the cache. The tag field of the CPU address is then compared with both tags in the cache to determine if a match occurs. The comparison logic is done by an associative search of the tags in the set, similar to an associative memory search, thus the name set associative. The hit ratio will improve as the set size increases because more words with the same index but different tags can reside in cache. When a miss occurs in a set associative cache and the set is full, it is necessary to replace one of the tag data items with a new value. The most common replacement algorithms used are random replacement, first in, first out, FIFO, and least recently used LRU. Thank you.